we call it the history of the area, the site of the area itself. For example, if you have a dead body, we have to figure out the physical of the dead body, and then we need to know the internal side of the body, the damages of the internal organs. So similar to this area, so they find out the geological features on the site area where it is composed of alluvial and marine sediment. So alluvial and marine sediments are categorized for very weak soil, very weak material or weak soil, and it was deposited during the Quaternary period as a result of predicted warm and cold climates and sea level changes. And from the image shown that the site area very close to the river that may have some changes in the water table. So in general, there are 7 soil layers within the upper 50 meter of soil below the ground surface. So the approximately 3.5 meter thick crust is composed mainly of field and silty clay, which are over consolidated because of desiccation. So desiccated crust overlies a 10-meter thick soft clay layer, which is followed by 16 deep firm stiff sill clay layer. So these informations later on being sketched by having the soil profile just to indicate the right dimensions of the soil profile for that particular site. At the same time, from the site investigation after the collapse happened, so they found out these are the soil properties for the site area for a unique way, and then the water content, void ratio, wind shear strength, and also cone resistant. The cone resistant QC is obtained from cone penetration test. So the cone penetration test can be carried out by static cone penetration test or by dynamic cone penetration test, where you can have the QC value. So the QC value having some sort of correlation to convert the strength of the soil at particular depth. So this is the soil profile from the 0 meter to the 50 layers, and also you can see that on few 10 meter above below the ground surface is very soft clay, and then at the last part at the 50 meter depth they found the fine sand. Okay, for the wind shear strength, so you can see that the strength is having very different values at 0 meter, and then it's getting lower when go in depth in 15, and getting increased at 25 and 20, 30, and slowly decrease at the 27 meter, and then it increased. So the variations of the wind shear strength of the soil show that inconsistency of the values of the strength. So linearly, generally we assume that the strength of the soil increased by that. However, since it has a different soil profile by having a very soft clay at the few meter below ground surface, so it shows that the bearing capacity and the strength of the soil is very low. So there's another reason why the failure also can occur at the particular site, or at the particular failure. And the same thing, but from different source, which was obtained from Shen ETAI 2014, indicates the same result for the building that marked as a number 7. So these are the soil parameters at the site. Okay, what are importance that you can have from here is show that the structural pi features. So the failure was occurred due to the soil structure interactions. The soil structure interactions is coming from the soil beneath the structure of the high-rise building, and the structure features is coming from the deep foundation that carry the load from the superstructure. However, again, the problem is not uh, due to the part itself, but the failure occurred due to the construction activities may not follow to the guidelines, and maybe lack of understanding by constructing on this PHC. Since they were using the pre-stressed high-strength concrete, may not be able understood by many people or many engineers or any site workers. So the constructions for this particular concrete parts must be very carefully taken by the person in charge, so that you can avoid any future failure. So it says that the PHC piles were steam cured under a pressure of 1.0 megapascal at 180 Celsius to improve early strength. So allowing for earlier removal time of the foam. So you can see that if I'm not mistaken, last week I have shown you the benefit and disadvantage using the PHC. So it can carry high strength of the material, and also but the advantage, not everyone know how to handle with this PHC parts. So it gives also the informations about the structural pile features. For example, each pile was 33 meter long and had an outer diameter of 400 millimeter and a wall thickness of 80 millimeter. So that's why when you read these two articles, some may say that it's a tube pile, or they may call it as a pipe pile, because the pile is some sort of hollow pile, because it has outer diameter and also inner diameter with the thickness of 80 millimeter. That's why it says that this is not very simple analysis as what we have as a solid pile in square or solid pile in circular. So the bars penetrated the clay layers and rested on fine sand as a bearing stratums. So as you can see from the soil profile just now, at the 50-meter depth, they found on the hard layer that was fine sand. So we believe that when the pile settled at the fine sand, it will be the hard stratum for the pile to rest on. Okay, the capacity of single pile was designed to be approximately 1,300 kilonewton, and the ground beams were used to connect all the piles and to transfer load from the superstructure to the piles. So the ground beam had cross-sectional dimensions 600 by 700 millimeter, and the upper 2 meter of the hollow PHC pile was filled with reinforced concrete and cast together with the ground beam to enable a robust connection, and hence referred to the reinforced zone. Okay, full-scale bending tests show that this type of pipe pile has a bending capacity of approximately 158 kilonewton meter under pure bending conditions. So this is also being proved by the authors having the simulation to obtain, is it the triggering moment caused to the failure is around 158 kilonewton. Okay, the next one is that similarly, again on the structure pie features, but I took from the Shan ETAL. These are the cross sections of the pile and also design properties of the piles. So I think that when you are dealing with the deep foundations, it's not easy as part as we understand the structure will be taken by the soil itself. So we have to take consideration by the structural properties, the strength of the structure itself, bending capacity, the tensile crack, and then the strength of the reinforcement. So these are the parameters of the pile concretes or PHC pile that must be taken into design considerations. That's why last week I shown you this is the bearing capacity of the pile and the difference equations for the structural pile capacity. So these are two different things that you have to take into account when you are dealing or when you are designing with the pile itself. Okay. The next one is on and this is just telling you what the standard PHC in Shanghai, China, that mentioned for the PHC type. So it says that for cast in place reinforced concrete, so the height of one story of residential building is typically about 2.98. So these are the rules or guidelines being carried out in China for this kind of the high-rise building and for cast in place reinforced concrete. And what is the limitations or what is the range of pressure or value of stress that can be tackled or can be catered by the building itself? Okay, the figure 4 shows that the layout of foundation piles before and after the collapse. So we are focusing the middle sections here because on the north of the collapsed building there was a dump soil, and at the start of the collapsed building there was an excavation site. So if you look at to this one, there were a lot of instruments being placed to the profile because they want to have the good view what they can get from the failure of the site. So these images show the positions of the part, and then the parts were inserted with the cameras and some other things. Okay. Okay, the next on the sketches, the sketch image show the high-rise building number 7, and then this is the pile embedded into the soil layers, and then the dump soil from the site having two stages. For the first stage, the height of the embankment was 4 meter, and then they dam another second stage around in 6 meter height from the first stage. So you can see that the stresses increase from the first to the second stage of the dam soil. So not intentionally knowing that will be increased to the lateral stresses. So the lateral stresses causing to the building collapse, the stresses coming from the north and also from the south of the collapsed building. Okay, the excavation. So this is the process, the construction activities on site. So they started by having the excavations at the particular depth, and there's some informations on the slope height for the embankment. And then the south side of the collapsed building, another excavation for underground garage. So this show the informations what will happen during the failure. So there were two activities involved. At the north was the dump activity, and at the south side was excavation for underground garage. So I have attached these two articles in the Future, so you can download these two articles in details for further reading. Okay, what's the important about these activities? Because the purpose of this article from Wang ETAL 2014, these researchers will try to simulate the conditions of the failure during the time building failed. So that's why they figure out what were the activities involved during the failure. So these are the things again, split it into two zones. The zone 1 for excavate to formation level as required, and then the zone 2 for unexcavated conditions. So it is shows that the plan view of the construction site. Okay, you can see that there were two dump site stages from the first stage to the second one, with having different elevations of the uh, site profile. Okay, from here, what he tried to explain is that the the chronology how the failure was occurred from the first dumping process, and then the beginning in 2009, and also to the next one until get the second stage of the excavated. So what it says from here is that the vertical loading from the trapezoidal dump soil was equivalent to a uniformly distributed loading of 94 kPa, assuming that the unit weight of the dump soil was 16.5 kilonewton per cube meter, and the size of the field slope was measured after the collapse of the building. So on the right side here, I try to simulate to calculate based on the stated statement here, where the surcharge field having the surcharge field around 63 kilometer kPa. And then 16.5, you can get the stress from the surcharge by multiply between unit weight of soil 16.5 kilonewton per cube times with the height of the field. Okay, if you can have a different height of the field, for example 16.5 you darab dengan 4 contohnya, and then 16.5 unit weight of the field darab dengan 6. So supposedly there will be additional stresses from the surcharge, so acting on the ground surface, and then the 10-meter thick soft stratum lies beneath the stiff grass. The soft clay could lose its bearing capacity because of the surcharge loading imposed by the dump soil. Based on the undrained assumption, the bearing capacity of the soft clay was estimated to be 5.14 SU. So 5.14 is the bearing capacity factor for undrained clay at phi equal to 0. So the SU, where it's get the SU, so you can see on the left side here, from the vein shear strength, the site investigation report at the 10 meter, and you can have the value SU equal to 25 kPa. So look at to the left side at the bottom image, figure 2, geological conditions and soil profile, natural water content, liquid limit and plastic limit. So from the graph, vein shear strength at 10 meter for soft clay, so the value SU undrained shear strength is equal to 25 kPa. So 5.14 times dengan 25 kPa, you can have 125 kPa. So for simplicity, the weight of the field and silt clay layers above was also considered to be a surcharge loading, which was estimated to be approximately 63 kPa. So under the circumstances, the total stress exerted on the soft clay stratum was approximately 157. So it shows that 157 kPa is larger than the pile strength in clay. Therefore, the pile failed. So kalau tengok kat sini pun kita dah nampak lah 5.14 darab dengan 25 yang dia can cater is 128.5. However, from the surcharge and then from the unit weight of the soil, 157 is larger than the pile capacity. So the stresses induced by soil given the structure pile failed. Okay, itu saya try nak explain lah. Tapi sebenarnya value ni from this statement actually referred to the schematic image and also from the soil profile and soil properties obtained from the site investigations. So the analysis, in order to analyze, we need few data from the field investigation and then the numerical analysis. Why it is used to analyze or to simulate the process of excavation and dumping, because we understood that these two activities brought to the collapse building. So they try to simulate on the simulations part, is it true or untrue for the hypothesis. Okay, this one similar. Okay, from here, just show to you the locations of fracture in pipe piles on the excavation at the southern side of the collapsed building. So this is the schematic image, show the positions of the pipe pile. And then again, for the simulations, the things are important for you to understand on the first part is the geometry model. You need to draw the right geometry size and dimensions that represent the problem, because we want to simulate the construction activities from dumping and excavation. So you can see on A and also and B. So A is the geometry model obtained from the software, and then B is a schematic layout plan. So this is the total depth soil profile, and here is the 13-story building. So on the north side is the dump soil, and at the north side is the dump soil, and at the south side is the excavation underground basement. So, and the other part about the simulations, you have to choose the right constitutive soil model. According to this paper by Wang et, they chose to model behavior according to the elastoplastic model with a Moore column failure criterion. So what is important about Moore column failure criterion is the first one, due to the analysis that you opt to have in some sort total stress analysis with assumption that the phi equal to 0. In this analysis, the undrained shear strength of the clay was determined according to the in situ vein shear strength. And the other parts, when you are choosing for Moore column failure criterion, is that the undrained elastic modulus of the clay was assumed to be 500 times SU. So the fine sand layer was modeled under drain conditions. So the effective drain models E effective or estimated from the below count number N standard penetration, and the retaining walls and pipe piles were assumed to be elastic, and their elastic moduli were 30 and 38 gigapascal. So The other parts important about the modeling, beside the pipe parameters, the soil parameters, is boundary condition. So here, the boundary condition is stated the length of the mesh in the lateral y direction was 170 meter. The width X and the Z were 160 and 50 meter respectively. And the boundary condition for the image is a roller boundaries were adopted for the vertical faces of the mesh. So the roller boundaries, meaning that you are allowed for vertical movement, but the lateral movement is restrained. That we call it as the roller boundaries. If you choose for the fixed end boundaries, that you are not allowing any displacement in X and Y also or moment. Okay, the other parts about the modeling, the retaining walls were simulated using 8-knot quadrilateral shell elements. The soil nails were modeled by ground anchors for both foundation beams and structural beams. 3-knot beams element were used. 118 piles were simulated using the embedded pile model, which consists of beam elements connected to surrounding soil. So this is if you are familiar with the geotechnical software such as Plaxis. I think that you understand what I'm talking right now. If you are not familiar with the practice, for example, there's something you might not understand what I'm saying. For example, more column failure criterion, and then the loading itself, the 15 node and the elements number. So these are the things, the features behind the simulations for this problem lah. So this model by 3 dimensions consisted of 65,439 elements and in total of 147 nodes. So the movement in all direction and all rotation was fixed at the bottom of the mesh. So the mesh, if you see on the top of this image at the left side, it will be different accordingly to the building or to the images or to the model you are focusing on. If you are focusing at the soil layer, so we're going to use the very fine mesh. If you just ignore the effect underneath a few meter below ground surface, so we can have the coarse mesh. So that will be different giving the answer for displacement, for example, and also for deformation. So the table one shows you the soil parameters used in the final element. So this is not indicate for the structural element properties. So the purposely for soil only. So you can see that the parameters are different accordingly to the depth. For the first layer, 0 to 1.3, and then to the last depth at 32.8 meter. So these are the parameters influence and the value of the soil parameters automatically to the final output from the simulations. So FS, FP, ultimate skin friction, ultimate end bearing, and the other rest parameters, I think that is suited for more column model. Okay, the other important part about Plaxis or any geotechnical, we need to understand the construction activities or the construction process. So it begins the construction sequence for the first one is the generations of initial stress condition. So the generation of initial stress conditions is the condition at the rest of the soil because it counted for the initial stress on the soil itself. Sama ada stress tu datang daripada gravity loads ataupun dia datang daripada sulfate of the soil. And the next sequence of the construction activity is to construct foundations and pipe piles and the building. The next construction is dumping of soil to a height of 4 meters for the first stage on the northern side of the building. And at the final stage of construction is to construct retaining walls, excavation, and dumping of soil to the final height of 10 meters. This is the second stage. In Plaxis, you have to determine these 4 steps first before you can have the final results. Okay, the final element analysis or the output. So the output state that from the figure 11 here, soil had been dumped to a height of 4 meters on the northern side of the building, the maximum bending moment of the pile reached approximately 58 kilonewton meter. So this value within the pure bending capacity of the pile. So it's okay lah, because the first slide yang saya tunjuk tadi, dia pure bending dalam 100 something, suggesting that the pile had likely remained intact at the point in the time. So yang ni tak menjadi punca kepada failure. Whereas the analysis of the simulations at the bottom of this slide at the left side indicate to you the maximum moment occurred at the middle sections at the 10 meter, where the maximum positive bending moment in the pile developed approximately 10 meter below ground surface, where the soft clay layer could be found. So it is show that the value of the maximum moment that triggering to the failure of the structure, pile structure. So this implies that the foundation parts of the building would have broken first at the depth where the interface between the soft and stiff clay layer was located. So kalau you tengok bahagian bawah ni, yang ni adalah yang analisis yang dapat daripada simulations, kemudian dia dikeluarkan dalam bentuk graf semula lah. Siapa yang pernah buat simulations, sama ada untuk geotechnical ke highway ke? So simulations ni bagus ni bila something yang complex problem kan, yang kita tak boleh nak encounter firstly, so we can do simulations sebelum kita start apa-apa activity lah. That just give you the idea of what's going to happen. Satu lagi, bila dia melibatkan complex problem, melibatkan few variables, parameters, with the simple hand calculation, mungkin cannot give you an answer lah. Okay, the next thing about the simulations from the activities of this collapsed building, the pure bending capacity of 158 kilonewton piles is also shown for ease of comparison dekat bahagian bawah ni. So you can see that the value of the pile along the excavation showed the same trend for pile near the dump soil, but indifferently lah for the value, because the embedded pile model, which actually consists of elastic beam elements, was adopted. The breakage of the piles could not be simulated in this analysis. So ni antara kelemahan lah. This is the reason why the bending moment kept increasing after the bending capacity was exceeded. Okay, apa yang kita boleh dapat lah from the failure? It just showed comparison on the north side and also the south side of the collapsed building. Firstly, kalau north side tu due to the dump site, so the uppermost fractures could be seen near the interface between the reinforced and unreinforced section, which were located approximately 1 to 2 meters below the original level of the pile head. So most of these failure surfaces were flat, implying that these piles failed under tensions. And then at the south side, the pile situated on the excavation side of the collapsed building, so the uppermost fractures surfaces were tilted and at angle and the concrete was severely damaged. So these fractures occurred mainly from the compressions. So nampak they are taken by two different. So kalau kita analyse on the beam pun, some beam akan ada section yang mengalami tension, the other side dia akan mengalami compression. So the largest bending moment was developed in the past on the excavation side of the building at the depth corresponding to the interface of the soft and firm stiff clay layers around 13.5 below the ground surface under the combined effect of excavation and dumping. So last week pun saya rasa saya dah tunjukkan antara benda yang kita boleh ambil from this failure lah. Okay, yang ni dia just show detail lah macam mana berlakunya structural failure from the analysis yang diorang carry out. So you can see that the process sequences of the failure. For the first one, the slip surface developed due to surcharge loading. Surcharge loading kita dekat bahagian utara bangunan yang runtuh tu. Kemudian pus broke at the interlayer boundary. So you can see that this is the potential slip surface. When there was a potential slip surface, so it shows that the weakness of the plane has developed in the soil. And then at the section C, or the image C, show that the pus broke at location of maximum bending moment and building tilted. And finally, in D picture, the building collapsed toward excavations. So it is very detailed explanation from the Wang et 2019 show the images, the process of the sequence failure from the beginning, how the surcharge loading triggered to the failure, and how the pore structure failed due to the moment at the interface or at the layer of soil within the few meter below the ground surface. Okay, these are the lessons learned can be obtained from this case study. The first one is that geotechnical engineers and contractors should be better trained to improve their understanding of the effect of surcharge loading on PHC pile. So the proper construction procedures and site supervision schemes should be explicitly spelled out. Engineers who design foundation in soft soil regions to consider not only the final loading condition, but also any temporary and transient loading conditions during the construction process. So that is come where when you are analyzing or simulate using the FlatSys or any geotechnical software, we can add on any sequence construction activities. In summary, but actually it's a lesson learned. It is evident that for this case history, the effect of the temporary embankment filling adjacent to the building may not have been properly taken into account in the foundation design or in the constructions. So a simple but important lesson is that in order to successfully design a foundation in a soft soil area, engineers not only need to consider the final loading conditions, but also any temporary loadings such as those that might arise from the storage of construction materials and construction generated waste soil. So last point here from the last slide and from the previous slide, agreed from both researchers by Wang et and also Shen et, meaning that during the time the construction activity, they were only considered the final loading without considered any additional surcharge or any additional activities being carried out on site. So that were the main causes, the problems of this collapsed building in Shanghai. So in summary, but bila saya baca beberapa artikel lah kan, kemudian saya baca news report, yelah kan mana ada orang nak admit. So the contractor of the site project pun dia tak mengaku yang company dia tak mengikut rules lah ataupun guidelines on site construction activities. So they kept saying that they were doing rightly, tapi bila some forensic team went to the site area, then they put back analysis, they found out there was some mistake and then on the design error. So bila cek balik, kebanyakannya akan ada problems failure berlaku disebabkan design error dan juga construction activities. So construction activity pun macam mana pun dia akan reflect balik kepada owner of the project or the contractor. So dalam kes ni, itulah nak nampaknya sebab banyak-banyak building dekat site tu ada lebih kurang 10 hingga 13 lah building yang sama. Tapi building nombor 7 je yang mengalami collapse. Yang lain tak ada mengalami collapse. So bila mereka buat penyiasatan, mereka dapati rupanya bangunan tu paling hampir dengan kawasan tambakan. Lepas tu in front of the building ada aktiviti construction yang lain. So menyebabkan dari banyak-banyak building tu saja yang tumbang. So itu conclusions lah from this case history for chapter number 3. So any questions before we proceed to the chapter 4? So the chapter 4, geotechnical application for returning wall actually, dia lebih kepada base excavation for returning wall. Any question?
Doktor, so contoh macam dalam design punya proses, kita actually kita punya apa ni, kita ambil consideration tak macam temporary loading ataupun surcharge? Sebab biasanya kalau kita design, kita ambil apa ni, final loading tu daripada building saja. Kita tak apa applicable dia punya temporary surcharge ataupun loading dan sebagainya.
Itu saya setuju lah. Memang selalunya kita akan ambil final loading lah. Antara point yang di-highlightkan oleh dua researchers tu yang macam soalan awak tanya lah. So macam mana pun you have to take into consideration. That's why bila kita buat hand calculations lah kan. Selalunya kita akan buat hand calculation for the final one, right? So when it comes to the something unpredictable or in sequence construction activities, it's come to you this kind of the modeling and simulations. By using the modeling and simulations or numerical software, you can estimate the intermediate construction activities that may encounter on site. Maksudnya bila kita dah buat prelim investigation lah, kita dah buat step awal. Bila kita dah buat simulation tu, kita dah tahu kalau kita buat kita calculate untuk first loading kita letak macam ni, macam mana kan. Kemudian dekat tengah-tengah tiba-tiba ada additional loading. So you can estimate or you can simulate or you can predict by having this kind of simulations. Tapi kalau you just use by hand calculation, selalunya memang kita akan estimate for the final one sajalah. Kita tahu berapa loading kita letak, mana kita calculate settlement contohnya. Tak pun kita calculate bearing capacity. Itu yang dia punya weaknesses antara hand calculation ataupun approximate method. So this problem, bila you tengok balik, something that cannot be measured by hand calculation or approximate method is come to the numerical simulation. But the problem about numerical simulations is not everyone understand how to use the software, right? In order to get the soil parameters pun nak buat interpretation masuk balik dalam software pun tak semua orang boleh faham parameters ni sesuai tak. Kemudian kalau contohnya Plexis ada method A, method B, method C. Method A for example undrain. Kemudian method B pun drain, but the drain and undrain that here represent different strength parameters of soil. So yang tu you kena hati-hatilah. So bila macam soalan-soalan awak tanya tu, bila part yang kompleks tu, yang transient loading yang kita nak kena estimate sebelum tu, so I suggest to have a numerical simulations lah for better predictions.
So dia soal parameter apa je yang dia tentukan dalam back analysis ni, Doktor?
Kalau you buat back analysis lah, mostly kita nak tahu macam case study yang ni kan, on part of the soal parameters dia tak ada masalah sebab dia dah ada report SI. Walaupun report SI tu maybe they got it from the side after failure. So the back analysis that they may had from here, the strength of the site during the time structure fail, itu satu. Kemudian dia nak tahu punca kegagalan bangunan tu dekat mana. So benda dah berlaku kan. So bila benda dah berlaku, kita tak boleh nak korek balik structure tu apa benda kan. So apa yang dia buat adalah dia estimate or dia buat simulation to predict the puncanya disebabkan oleh tanah ke, bearing capacity ke, strength rendah ke, ataupun puncanya disebabkan oleh structure. This problem is having interaction between soil and structure. So bila dia buat numerical simulations ni, they found out the problem is came from the structure itself, the structure capacity. Structure capacity kat sini triggering by the moment yang terhasil daripada stresses induced by the north side and also the south side of the construction activities. So analysis yang diorang buat ni juga disokong oleh observation being carried out on site itself. Maknanya dia pergi ke site. Sebenarnya bila you buat simulations dia akan ada hypothesis. Contoh hipotesis pertama, you assume failure disebabkan oleh soil. Hipotesis kedua, failure disebabkan oleh structure. Tapi sebelum you nak buat hipotesis ni pun, you kena ambil raw data from the site, right? So for this area, bila dia pergi site, so dia dapati daripada jenis runtuhan, lepas tu surrounding building pun, dia nampak asal kepada masalah tu datang daripada dump soil. Dump soil tu created to the additional stresses yang menyebabkan failure to the structure that having moment interlayer between the structure dan juga soil. So itu yang hipotesis tu terhasil. Maknanya dia disokong oleh apa hasil yang dinampak pada tempat kejadian yang dah berlaku kegagalan tu. So dalam bila buat back analysis tu, maklumat daripada site itulah yang menyokong kepada analisis ataupun calculation yang seterusnya. Okay. Am I answering your questions, Amir?
Ya. Sebab kalau macam pavement kan, kita bila dah dapat dia punya yang modulus, so nanti kita akan compare dengan yang modulus yang lama, dan kita mau masuk dalam formula formula apa tu? Formula tu dia akan reflect kita punya untuk design life. So bila design life macam untuk pavement more than 10 years or 7 years yang kita pick, so dia kita akan pakai calculation untuk yang modulus tu lah.
So sama juga dengan soil.
Oh, sama jugalah.
So dia nak dapatkan, you akan ada strength soil masa fail. Kemudian you mungkin ada strength soil before failure. Before failure ni selalunya sebelum start construction tu, diorang dah ada site investigation report kan. So bila you buat back analysis dalam software, contohnya dia ada satu method kita panggil shear strength reduction technique. So the shear strength reduction technique incorporated in Plaxis software tu, geotechnical software tu, they can estimate berapa nilai strength during failure occurred tu. Dia dah boleh bagi tahu value dia berapa. Maknanya kita doing the back analysis, we estimated from the failure to the original one. So kita nampak lah, originally soil strength banyak ni. Lepas tu bila dah berlaku failure, of course there will be reductions or we call it residual strength. So residual strength itulah menyebabkan strength makin lama makin sikit. Due to the other reasons jugalah. Contohnya dah mengalami excavations, and then dia dah mengalami weathering process. So for example, in case study here, untuk this particular case history ni, bila dia back analysis yang difokuskan kat sini adalah mencari punca kegagalan berlaku. So dengan adaptasi kepada activity construction. Activity construction yang diambil kat sini adalah dump site dengan excavation. Sebab dia nak estimate kan from the back analysis process tu, from these two activities ni, failure tu betul-betul berlaku kat mana? Adakah dekat soil ataupun interaction between soil and structure? Ini yang orang kata complex problem bila you dealing with the pile structure, kemudian you dealing with the parameter structure lain, kemudian parameter soil berbeza. Kalau you nak buat simple calculation analysis, we just take it out as a final assumptions, final data, final value and to the final loading or final output. Tapi kita tak akan ambil kisah pun. In between tu ada tiba-tiba tambahan loading contohnya. Tambahan extra. So yang kita design tu yang for the final one. Bila datang in between tu yang kita tak jangka-jangka tu selalunya boleh menyebabkan unexpected failure ataupun unexpected result lah. I can say that that's good about software, but a lot of limitations lah when you are using the software. For the simplest one, talking about the parameters of the material, sama ada pavement ke, subgrade ke, salt ke, you can have that one. Back analysis, estimate strength dia ke, stiffness dia ke. But again, ada benefitnya, kita bukan sekadar tengok parameters material tu saja. Kita juga boleh tengok on part of the construction activities. That's why bila failure berlaku, ada dua je sebab dia. Sama ada construction activity tu tak follow guideline ataupun design error. Design error ataupun calculation error. So itu yang common orang kata apa? Common mistakes lah. Causes of the failure. Okay, we break 5 minutes before we proceed to the next chapter 4. Nicole Highway in Singapore. Have you heard on that case study? So we break 5 minutes. We're going to have the next one. Okay, I'm going to continue with the next chapter 4. So it is on Brace Excavation Collapse and Nickel Highway in Singapore. So again, there are 3 learning outcomes. For the first one to discuss, this should be on the brace excavation failure and to evaluate the failure cases using relevant theory. And the next one to propose mitigation measures related to foundation failures. So before we go in details about the failure of the brace excavations, let us have this slide. A second. Okay, so next on this slide, the case descriptions about the site. So the island, city-state plan to have the mass rapid transit railway network in Singapore. So the constructions of a new 33.6 kilometer long underground circle MRT line started in 2001. So the costing about 6.7 billion. And the first stage of this construction was 5.4 kilometer long and was subsidized into two contracts, C824 and C825. And you can see on this right side of the slide shows that the locations of the island and also the first stage of the constructions. So yang ni adalah interchange untuk pembangunan jalan raya lah untuk tujuan MRT. And then the failure occurred around 3:30 p.m. on April 20, 2004. The 33.5 meter deep cut and cover excavation required for the constructions of tunnel between Nickel Highway and Boulevard stations. So the red circle in figures 6.1a collapsed. So the collapse was catastrophic, resulting in 4 fatalities and a lot of damage. So which delayed the completions of the CCL1 stage by about 4 years. So during the time, if I'm not mistaken, this very gave huge impact on the construction activities in Singapore, because Singapore was well known as the well-developed country, and also the technologies, and all, we assume that all the activities construction were very tremendous being carried out in the Singapore. However, when the failure occurred, it's become bad repetitions to the Singapore and make it the delay of the MRT. And from the Singapore government committee of inquiry, they came to the conclusion, which in computer dominated age sound, a wrong use of numerical modeling in geotechnical design, together with some structural errors, were the main causes of the Nickel Highway collapse. So when it says that the numerical modeling in geotechnical design is very important, the persons or the user of software understand what are the models being adopted in the analysis and also the simulations. And the statement here is not detailed explain what were the geotechnical errors in that particular analysis before the construction started. It's just a state that the wrong use of numerical modeling. And from this article also, or from this topic, it's not mentioned that what were the geotechnical errors on this part of the design. It just explain the design and constructions from the beginning of these activities. If you look at to this figure 6.3, the excavation returning structures, where the diaphragm wall used at these sections of the cut and cover tunnels were 0.8 meter thick and penetrated 1 to 3 meter into stiffer strata at the depth of about 40 to 45 meter. So the construction activities were constructed using the bottom-up method. So the bottom-up method explained through this image of the diagram. And also, the 2 layers of the jet grout slabs constructed using interlocking jet grout bars were also installed after construction of the slurry walls to minimize deflection and ground movement during the excavation work. So the failure is happened due the failure happened on this diaphragm wall, because the wall cannot restrain from the soil movement. And then the excavation was kept open by a strut system comprising of steel king posts, whalers, and 10 levels of strut. The struts were spaced at 3 to 3.5 meter vertically and 4.0 meter horizontally. So the width of excavation was about 20 meter and it was about 33.5 meter deep. So it this image or this figure for 6.3 explains the statement above on the design and constructions. So this is the intersections of the road being carried out, and the sections at this right image show to you the collapsed panels of the route for MRT here. Not to forget, during the construction, there were many equipments for monitoring, such as settlement marker, and then the vibration wire piezometer, the inclinometer. So all these instruments were placed in the area because to estimate the movement of the wall and then the movement of the soil from using this gauge and the instruments. Okay, an extensive monitoring system was installed. It included more than 2,000 monitoring instruments, settlement markers, inclinometers to measure soil and water displacement, vibrating wire piezometers to measure pore water pressure, the strain gauge, and load cells to measure the strut loads. So the reading from the inclinometer I65 and I104 and strain gauge and load cells in the strut are crucial for understanding the cause of excavation collapse. So this figure 6.5 showed you the displacement of the southern wall in time. So you can see that the maximum displacement occurred on 17 April 2004. So you can see that initially the displacement 0, and then the displacement keeps increasing when they constructed at the third design level around 359 millimeter. So the collapse. So according to COI reports, the warning of the approaching collapse were present from an early stage, but these were not taken seriously. Indeed, as early in August 2003, it became clear that something was wrong with the design. First, in the launch shaft for the tunnel boring machine across the river Earth from the collapse area, the measured wall deflection exceeded 500 millimeter, while the calculated design level was only 190 millimeter. From here, actually, they dah bagi early warning lah, early sign warning, but no one cares about the warning. So this caused damage to the retaining walls, ground settlements, and crack at the critical field nearby. So apa tujuannya bila kita letak instrumentation? Because we want to observe the reading, on-site reading, and what we are estimated to from our design and analysis. The somehow something may not unpredictable on-site versus off-site. I mean that when you are design and analyze, you may say that your design is correct. But once you encounter or once you go to the site, you are facing obstacles, different things unexpected. For example, the changes of water content, the changes of groundwater level, and then the sudden displacement that will bring you to difference what you have calculated earlier. So it showed that in early January 2004, the design deflection level was exceeded and cracks appeared in the retaining structure in the cut and cover excavation west. So, and these are the explanations how it was started to the bridge excavation collapse. An extensive monitoring system included more than this 2000, as mentioned just now. And then the deflection was accompanied by buckling of hollow stiffness plates, so which were replaced by C channels starting from the 7th level. So unfortunately, this not help, and at the end of March, the new design level was exceeded again. Another back analysis produced another revisions of the design level up to 359 millimeter, which nevertheless, when the last measurement was taken on the day of collapse, was exceeded by much as 22%. So you can see that it is dia bukan estimated lah, but dia dah bila dia dah buat some projections, dia dah nampak by the day of collapse, so displacement dia dah makin tinggi daripada 359. Dia calculate lagi, dia buat back analysis, they found out the settlement can increase go up to the 445 millimeter. Of course, that triggering to the failure lah. And again, failure tu berlaku lebih kurang pada 3:30 petang. Sections of temporary diaphragm wall supporting the excavation adjoining had collapsed. So inilah triggering point explanation, the chronology how it was started. So sebenarnya early sign tu dah ada tapi tak diambil berat lah. So you can see the buckling of the C sections and for the stiffener plates and also to the C channel. In the collapse area itself, the inclinometer I014 indicate that the original design level of 145 millimeter in the southern diaphragm wall was exceeded as early in February. So maknanya pada tempoh tu pun dia dah ada dah. At the moment installations of the 6th strut level was in progress. Or never noticed during this the construction activities pun sebenarnya dia dah berlaku failure dah. Tapi no one take it into seriously lah. Okay, yang ni pun sama juga. Okay, Okay, it is combined together. This error resulted in considerable under design leading to the failure of the returning structure. So the replacement of the stiffener placed by C channels changed the mode of failure from ductile to brittle. So here just to show you the failure mode of the returning wall. Yang ni dia tunjuk macam mana value for the undrained shear strength by having the back analysis. And then what you need to do is for this problem I just want you to have your time untuk go to this link, make it your short notes about the wall deflections. So it is a reflections to what you have watched from this slide lah, on construction worker nearly dies after the trench wall. In details about the theory analysis on this particular Nicole Highway brace excavation will be resumed next week, cuti next 2 weeks. Boleh? InsyaAllah. Okay, this activity saya announce dulu malam ni. Saya akan post dalam YouFuture. You just submit your short explanation on this YouTube. Kemudian your short explanation tu you boleh tulislah dalam atas kertas ke, you nak buat PowerPoint ke, kemudian you upload dalam YouFuture. Nanti saya akan share link YouFuture untuk you upload your punya short notes or reflections from this YouTube channel. What you have watched and apa yang you can get from here lah. And saya rasa banyak je kejadian dekat Malaysia, contohnya kan any other construction site yang mana workers die during the construction activities. Contohnya lah kan tiba-tiba ada soil movement, tak dapat nak lari. Itu yang biasa kita dengar kat Malaysia, ataupun tiba-tiba tanah runtuh kan. So banyak yang sebenarnya di luar jangkaan lah kan. Kita nak salahkan pada design and error ataupun construction activity tu benda yang selalu sangat dengar lah, tapi tak lupalah ada kuasa lain lah yang mengawal kepada segala benda lah. Tapi apa yang penting yang saya boleh nampak lah, yang try to highlight in this Nicole Highway brace excavations adalah the safety first. Safety at the construction site tu amat penting untuk diambil berat lah. Kalau ikutkan area Singapura ni mostly area yang dekat dengan kawasan laut kan. So mungkin bila dia buat constructions at that particular, dia akan ada cut and fill, dia ada some reclamation area, mungkin ada part-part tu yang dia tak ambil kisah lah. And during that time, bila 2004 lah kan, dengan limitation knowledge on numerical modelling, not everyone understand how to model or how to do simulations in software, for example. They can also create to another problems lah. For example, from this reported, it says that the committee claim the excavation brace excavation collapse due to the numerical modelling. So I believe that it was due to the engineer who may not familiar with the software environment, for example, because in order you to hands on the simulations or software, the first one you need to understand the environment of the software. You nak kena faham dia punya behind of the software, dia punya teori adopted, apa teori yang dia kena pakai, kemudian calculation dia. So that's not easy lah, but somehow problem yang kompleks tu nak tak nak memang kena software lah. So back again lah, when you want to use software as part of your analysis too, bear in mind. Okay, that's my conclusion for tonight. I'm going to post the activity tomorrow in the YouFuture. So anything regarding about this week activity, you can ask me in the WhatsApp ataupun apa-apalah yang berkaitan. So kalau you tak faham on this part, you can ask me also. Okay?
Doktor saja tanya dia punya apa deadline ni bila dah.
Okay, about deadline you don't worry. Sebab saya akan buka selalunya seminggu lah. Minggu depan cuti. Lepas tu paling lekeh lah. Busuk-busuk pun saya akan open lah sampai habis semester. I just want to
Busuk
have
sedap.
your reflections. Ha? Apa dia?
Dah yang busuk, yang baby busuk tu macam okey tu.
Week 14 lah. Janji hantarlah. Maksud saya macam tu lah.
Alhamdulillah.
I tahu you kerja. Benda ni kan just on reflections tau. Because when you heard too many failure cases lah, different failure cases will have different mitigations and also different lesson learned. Not every failure cases will give you same lesson learned. I just want to have your personal opinion regarding on this case in that particular link given here. Saya nak tahu apa yang you faham. Kemudian macam saya tunjukkan few cases before this. First Transcranial Green Elevator. Kemudian yang baru ni habis in Shanghai. The new one here in Singapore. So you can see there were different construction activities involved, different theory and analysis involved. So there will be different lesson learned and mitigation carry out. So on yourself from after you watching this video YouTube, so what you can do or what can you explain by having these reflections through this video? Just want to know your personal opinion regarding this failure. Is it safety measure ke, tak ambil kisah ke, ataupun design error ke, always back design error ke, ataupun construction tak follow guidelines ke. Itu I want to hear from your personal point of view. You can write down and post in the near future. Okay, not to worry, I will open until week 14.
Terima kasih doktor.
Okay, we finish our class tonight and the class will be resumed after break in week 10. Ya, Assalamualaikum dan selamat malam.
Terima kasih doktor.
Terima kasih.